We often picture space-time as a rigid 3D grid with a ticking clock. In reality, this geometry is fluid, governed by one mathematical quirk. This is the standard Euclidean inner product. By squaring and adding the spatial components, the math guarantees that the distance between any 2 points is a positive number. Lorentzian geometry alters exactly one sign in that foundation. The first plus sign becomes a minus. That substitution removes the requirement for universal positive distance. The squared norm of a vector now evaluates to a negative number, 0, or a positive number. Translating this algebraic change into physical geometry reveals a 3D dual cone structure. This is the Minkowski light cone. In 1909, Hermann Minkowski proposed that space and time form a single geometry designed to preserve this new quadratic form. The Lorentzian metric functions as a cone-valued discriminator, assigning a causal type to every vector in a tangent space. This typing discipline dictates the global behavior of matter and light, serving as the foundation for the architecture of general relativity. At every infinitesimal point in spacetime, your ability to navigate is dictated strictly by the local boundaries of the nullton. This diagram models that restriction. The vector trapped inside the upper boundary is timelike. This represents the mathematically allowed history of a massive particle or an observer. Vectors tracing the surface of the cone are null, while vectors sitting outside the cone are spacelike. The causal type of these directions is invariant. No physical rotation or Lorentz transformation can turn a time-like history into a spacelike one. Light travels along the null boundary. Because the metric evaluates these vectors to 0, light accumulates exactly 0 proper time during its journey. The cone is the absolute local limit of physical influence. You must check your direction against the boundary before any motion is possible. We can observe how curves behave differently by comparing two types of space. Left is a standard Riemannian surface. Right is a Lorentzian spacetime. On the Riemannian side, a geodesic pulls taut between points A and B, locally minimizing the physical distance. In Lorentzian geometry, the behavior is reversed. The straight vertical line connecting A and B represents an inertial observer, and it locally maximizes the proper time experienced between those two events. If a second observer takes an accelerated detour, this time separation equation shows they accumulate less proper time. This is the reverse triangle inequality. It's a formal statement that an intermediate detour reduces the maximum time separation between endpoints. Physically, this means that any acceleration reduces the agent experienced between two fixed events. Albert Einstein described this as the twin paradox. The twin who takes the accelerated path returns younger because their journey accumulated less proper time. The universe rewards direct, inertial motion with maximal aging. Taking a detour forces you to experience less time. By tracking individual causal curves, we can begin to map the global architecture of a universe. This tracks regions of influence. Point P emits a forward-facing cone, its causal future. Point Q emits a downward-facing cone, its causal past. The intersection creates a causal diamond. It contains every event influenced by P that can simultaneously influence Q. In Lorentzian geometry, the compactness of these diamonds determines the stability of the space. They serve as the primary tool for analyzing global behavior. A spacetime satisfies a condition called global hyperbolicity if it contains no causal loops and all of its causal diamonds are compact. The Bernal-Sanchez splitting theorem proves that a globally hyperbolic spacetime can be sliced into smooth chronological layers, organizing the universe into a stable evolution problem. But mass concentrations can break this stability. Roger Penrose demonstrated that trapped surfaces inside black holes cause this smooth architecture to fail. Stephen Hawking showed that gravitational collapse can force causal geodesics to end abruptly. These incomplete curves are the primary mathematical indicators of a singularity. Smooth mathematics maps an ordered universe, that the extreme physics of singularities cause this smooth grid to break down, necessitating a more robust mathematical language. When classical general relativity encounters extreme physics like shock waves or singular densities, the smooth, differentiable metric tensor completely fractures and breaks down. At this level of irregularity, we can no longer use the standard tools of calculus to prove geometric facts about spacetime. Michael Kunzinger and Clemens Salmon developed Lorentzian length spaces, abandoning the smooth manifold grid entirely. We replace it with a causal pre-order, a directed network defining which points can legally influence others. We then add a time separation function, assigning scalar values to these paths to establish the maximum proper time between events. Here, a geodesic isn't the solution to a differential equation. It is simply any causal curve realizing the maximum time separation between endpoints. Stripping space-time down to a relational graph of cause and effect allows researchers to mathematically analyze the limits of non-smooth metrics. This framework provides the stability needed to study singularity formation and low regularity models, where classical differential geometry breaks down. Synthetic spaces present a unique challenge. Because the Lorentzian metric lacks a positive distance function, measuring how different spacetimes converge requires a new approach. This is the Null distance formula. It uses a defined time function to extract a positive metric from a causal structure. By calculating lengths of piecewise causal paths, researchers analyze convergence in structures that lack standard physical length. On the research frontier, mathematicians are now using optimal transport to synthesize time-like curvature bounds directly from probability measures. Ultimately, our entire physical understanding of motion and macroscopic influence is strictly defined by these unyielding causal boundaries. Lorentzian curves are the traces that test the causal order of the universe. They probe the structure of time separation and physical influence. By decoupling causal order from smooth geometry, mathematics shows that the fundamental architecture of spacetime, cause, effect, and proper time, remains intact even when the differentiable metric ceases to exist.